Hello and welcome back to Series and Sequences. As always, I want to thank all the nice people that support this channel by liking and subscribing. In today's part 5, I want to discuss the finite sum of a geometric sequence and show you where the general formula for the sum of n terms comes from. So let's get right into it. Let's say we now want to add up all the terms of a finite geometric sequence, meaning that the geometric series. So Sn, which denotes the sum, is now u1 plus u2 plus u3 and so on. An alternative way to express the sum would be all in terms of just u1 and the common ratio. So now u1 plus u1 times r, then plus u1 times r squared, then plus u1 times r cubed, and so on. Now, let's say we multiply both sides by our common ratio r. So now we have two expressions for the sum. And suppose we take the second one and subtract by the first one. So basically, we use r as n and subtract it by Sn. You can probably notice that most of the terms will cancel out, like the ones I'm crossing out right now. However, the ones left would be the last term of our geometric series and the first term u1. Now, from the last video, we know that the last term can be expressed as u1 times r to the power of n minus 1. However, in this case, we multiplied by another r, so that means the minus 1 vanishes, and this would be our last term. Simplifying both sides of our equation, we would get r Sn minus Sn is equal to u1 times r to the power of n and minus u1. What we can do next is factor out like terms. On the left-hand side, we can factor out Sn and we would get r minus 1. On the right-hand side, we can factor out u1, and in the parentheses, we have r raised to the power of n and minus 1. Finally, I can divide both sides by the r minus 1 term here, which would give me Sn is equal to this formula right here. And this is the general formula for the sum of a geometric sequence with finite terms. You can usually also see another expression for the sum, which is written as u1 times 1 minus r raised to the power of n divided by 1 minus r. Now, these two expressions are the same. You just notice that the 1 and the r switch positions. However, they switch positions in both the numerator and denominator, so that means there will be no sign changes in case of negative values. So now that we know where the formula comes from, let's take a look at an example. Let's say we're given a geometric sequence where the sum of two terms is 20 and the sum of four terms is 1640. And now we're tasked with writing the general term of two possible geometric sequences. So let's break this down. Let's begin with the sum of the first two terms. This can be expressed as u1 plus u2. An alternative way to express this would be u1 plus u1 times r. So basically this is u1 times 1 plus r. Moving on to the sum of the first four terms, here we can employ the formula that we discovered. The sum of four terms is u1 times 1 minus r raised to the power 4, all of this divided by 1 minus r. And here we have two unknowns, mainly u1 and the common ratio, and we have two different equations, meaning we're solving a system of equations, and we can do this by dividing S4 by S2. Now S4 is 1640 and S2 is just 20. Their division gives us 82. Now let's divide their equations. When dividing their equations, the u1 are actually going to cancel out. However, for now, nothing else will cancel out. We get 1 minus r raised to the power 4 in the numerator, and we get 1 minus r times 1 plus r. You can see on the bottom, we can simplify it using the difference of squares, so this gives us 1 minus r squared. Here on the top, we can actually expand it using the difference of squares. So what we get is 1 minus r squared times 1 plus r squared. And then when divided by 1 minus r squared, these two factors will cancel out, and all we'll have left is 1 plus r squared. So now that means that 1 plus r squared can be equal to 82. Thus, r squared can be equal to 81, so that means the common ratio can be plus minus 9. Thus, we're tasked with finding two possible geometric sequences. Now we have to explore two cases when r is positive 9 and when r is negative 9. Through them, we can find the respective first term of each geometric sequence, and we can do this using the sum of two terms formula here, mainly this part u1 1 plus r, which is equal to 20. So when r is going to be 9, u1 in this case is going to be 2. However, when r is negative 9, we get 20 over negative 8, so simplified is negative 5 over 2. So for the first case, the general term of the sequence is going to be un, which is equal to 2 times 9 raised to the power of n minus 1. For the negative common ratio, or the second case, the general term of that geometric sequence is going to be negative 5 over 2 multiplied by negative 9 raised to the power of n minus 1. And here we have found the two possible geometric sequences. So that's enough for today. In the next video, we're going to speak about infinite sums. And there's going to be another sum formula that I would like to show you. So I hope to see you there and have a nice day. Bye.